friends, once again related to the second module and related to the half wave rectification as well as the full wave rectification. But this is not about the principle. It is about the analysis of a half wave and a full wave rectification. Like what happens. You remember I had already told you many a times, like half wave rectification will give us an efficiency of 40%. Or for a full wave rectification, it will come around 80%. Then why? Like how do I prove that? So all those things should be dealt for today. And there will be some numericals also. If time permits, we will touch upon that. Otherwise, we'll come back on next day's class and we'll touch upon some numericals before starting the third module. Most probably, if I'm not wrong, with the time we have, we will definitely have 1 and 2 module, and there will be a portion of the third module that I think will be there in your syllabus. And if everything goes well, I might take the quiz just after Cat 1 is over, not before that. Okay, so just for your information, after the Cat 1 is over, because why I do it usually that the syllabus will be the Cat 1 syllabus. So you already will be prepared with that. You have already are familiar with that topics, those topics. So that's why the quiz usually what I observe, people will score a little well compared to if I take it right now, in fact. All right. So because you are not prepared at all. So that is one of the things that I thought of telling you today itself. So let me just share my screen and let me just show you the things that is important. All right, so I would request all of you to keep a track of this particular class at okay, because this is all no PPT, nothing is there, and this is only about the class notes. All right. So if you observe the left-hand side diagram that we are looking at is basically a single-phase half-wave rectifier that we all know, and already we have discussed this multiple times in our labs as well, and we have implemented that as well. And if you see the right-hand side diagram, the sinusoid figure that we have, this is also a theoretical figure that we are talking about. But ideally, we have also found out that this can be also derived or proved through the simulations as well. So that we all agree. Now let us find out some of the parameters that we can extract out of this half wave rectification, because the same parameters we are also going to evaluate for the full wave also, but that will be little less time consuming because we are already deriving it or we are already establishing it in half wave. Remember that full wave is nothing but a double-sided half wave in a way. All right, so that's why it will be little bit simple in case of in case of full wave rectification. So the first thing that we need to understand is that what are the assumptions. So the input sinusoidal, that we have, okay, that is a voltage AC supply that we are actually providing. So that is given by, suppose VI is equal to Vm sine omega t. All right, so you can see the first figure A if I call it, and if I call this as figure B, so figure A is actually indicating the AC supply that we are having. So let me just put this as equation number 1. All right, now the diode current or across the load that is up with respect to this will be given very easily as, so I will write diode current, okay, of the load that we are considering will be given by IT equals Im sine omega t for, please observe carefully, the range is 0 to omega t less than pi, and it will be 0 for pi to, if you observe the graph very simply, we can observe this, that during this period pi to 2 pi, there is no voltage that is associated with it. So naturally, there won't be anything because it's a reverse bias condition that we are considering. Remember, this is we are doing for the half wave rectification. We are doing it for the half wave scenario. All right. So these are the two scenarios that we are having with respect to current. So the peak current, the equation for peak current, maximum peak current, we call it maximum peak current, which is given by Im. Just keep the nomenclatures as it is. All right. So I'll keep this as equation number 2 maybe, and this as equation number 3. Okay. So Im is given by the maximum potential, that is Vm, divided by RF plus RL. So please make a box like this. All right. So this is called as the maximum peak current. Suppose a circuit is provided to you and you are supposed to find out what is the peak current of the circuit. So it will be given by the maximum amplitude of the voltage divided by RF plus RL, where RF stands for diode forward resistance, which will be very small and almost negligible, and RL is indicating the load resistance. All right. Usually we'll neglect this RF most of the time. That's why we will consider it as Vm by RL is equal to Im. Now let us try to find out what is the average DC current. All right. So this we can find out. So average DC current is given by the average DC current is given by. So this is again from the formula itself we know, but still for your recap, I'll tell you. So IDC is usually I average. It's equivalent to I average of the total current, whatever we have. So that is given by 1 by T for the time 0 to T, IT, dt. All right. So this is we are integrating the total current over the period of time capital T, and that will be the average current. And that average current is nothing but the DC current that we are considering for the scenario. All right. So if you substitute this IT from the equation 2 and 3, okay, if you substitute over here, so the scenario would look something like, I'm not diving into details, but anyway, the time period over here is 1 by 2 pi, because you can observe the maximum is 2 pi. All right. So we are giving the time as 1 by 2 pi, 0 to 2 pi. All right. IT T omega T. So we are replacing it by omega T because we are considering 2 pi over here. So this, I think all of you would know it, but you don't need that, to be honest. This whole thing you might not be needing, but this is the how the derivation should look like. So which is given by 1 by 2 pi integration 0 to pi Im. Why I'm writing this? Because this is the only current equation we have. Omega T, T omega T, plus there will be another integration between pi to 2 pi, but this will be 0 d omega t. All of you agree to this? Okay. It dt, we are just segregating it into two halves because the current in our case is not a consistent one. There is a range given over here. So between 0 to pi, there is a current, but pi to 2 pi, there is no current. So that we are substituting over here. And finally, after all this calculation, okay, all the above calculation and substituting everything, your IDC, please make a note of this only. Okay, this is what is important, is coming as Im divided by pi. Please make a note of this. So the average DC current is given by Im by pi. So maybe I'll just keep this as 6 as equation number 6. So I was having 1, 2, 3 over here. Then maybe I'll keep this as equation number 5. This may be equation number 4. And finally, this is 6. All right. So this will be useful later on when you're referring to it. So suppose now you have Im by pi. So can I write this equation Im by pi with the help of equation number 1? Okay. Over here. Maybe I'll write, all right, this instead of keeping this as 4, I'll keep this as 4. So if you consider the fourth equation, Vm by Rf plus RL, this was equal to Im. So this I substitute over here. So Vm by pi into Rf plus RL. All right. So this is another form of IDC that you might keep a note of, because in many questions, different ways the questions will be presented to you. For example, if your question gives you that the maximum current for a particular network is Im, find out what is the average DC voltage. You can directly substitute and you can get the answer in this equation, equation number 6. But if you look at equation number 7 over here, this is where you actually have to know the maximum amplitude. Suppose a spectrum is provided where the sinusoid has a Vm, suppose 5-volt supply we have mentioned. So that through which you actually can calculate the average DC over here. Okay, so this is a very important assumption, very important junction actually, that we are calculating IDC, because if I know the, sorry, if I know IDC, then we actually can find out what is VDC. All right, so we can find out what is VDC as well. So VDC is equal to nothing but, can anyone tell me IDC? What will be then?
Into RL.
RL, yes, IDC multiplied by RL. So IDC is again the same way we can write VM by pi RF plus RL multiplied by RL. Okay, and after a little reshuffling of the whole setup, we can write final result VDC equal to VM by pi 1 plus RF by RL as equation number 8. All right, so this equation gives us the eighth equation will give us the value or the VDC which we are supposed to get, and you can observe that VDC will not be equal to VM by any chance. Okay, so VDC will definitely have some less. Remember in the lab when we were doing it, we found out that the output that we were generating, it was coming little less compared to the amplitude of the sinusoid or the amplitude of the input. So that small little segment is because of this factor RF by RL. Although RF is very small and it's negligible, but the effect of the load resistance will be there. And that's why VDC will be little less compared to the maximum voltage. All right. Now, in that term, we can also find out what is the power. Okay, we can also find out what is the power, DC output power. So we can say PDC is equal to IDC square multiplied by RL. So that is VM square by pi square RF plus RL whole square multiplied by RL. All right. And after a little bit of manipulation, you can observe that directly we can write that PDC is equal to IM square into RL divided by pi square. Okay. So this will be the total power that is dissipated as DC power. All right, so this is another equation. Maybe I can write it as equation number 9 maybe. So we have found few of these important equation. If I go back once again, one of the first equation is the maximum peak current. So please make a note of this, VM by RF plus RL. And we can also find out IDC, which came around IM by pi. Very small equation, but very important equation. We'll find that in fact later on. And also we have another version of IDC, which is in terms of VM. And finally, we found out what is VDC and what is PDC. So this is what we have observed in terms of IDC. Now, if I can try to find out what is the RMS values, okay, root mean square values of the current and the voltage associated with this. So what I'll have to do, we have to find out. So if suppose I want to find out what is the total power. So if I want to find out what is the total power, okay, total power will be P, or if I consider the not the total power but the AC power, total AC power. I'll write it this way: total AC power. That is when we are applying the supply or the V in, then what will be the power dissipated? So the total power will be given by PD plus PL. Now what is PD? PD is usually considered as diode dissipation. Diode dissipation power. All right. So this PD is the diode dissipation power, and this is basically the load power. Okay. So this is about the load power. Now, in both the cases, one very important parameter is required, because when you are calculating the total AC power, you can't do it using the DC voltage or DC current. What you have to do, you have to write the equation in terms of the RMS voltage, RMS current. So RMS square multiplied by RF. So this will be my power dissipation, plus the load current will be I RMS square multiplied by RM. But IRMS is unknown to us. IRMS we have not found out. All right. So we have to find out a way in which the IRMS can be found out, and that IRMS is nothing but the square root of the IDC value that we have got. All right. So in a way, I'll just write it in a footnote over here. So IDC, the IRMS rather, is equal to square root of IDC. All right. So the or not exactly IDC, or rather I would say not exactly square of IDC. I would write the whole statement maybe. So it will be 1 by T, okay, summation 0 to T I square T dt. So this will be the equation actually. All right. So this IRMS. So again, you remove this or integration and the square root part. The final expression of IRMS comes as Im by 2, or we can also write Vm by 2 into Rf plus Rf. All right. So this you please keep a note of it. This is the RMS value of the circuit. So we get a RMS because the RMS current is required because we have to substitute this over here as well as over here. Okay, so that is one of the reasons why we are trying to find out. So if I substitute over here with respect to Im by 2, because this is a little simpler, smaller expression that you are having. So this will be written as Im square by 4 multiplied by Rf plus Im square by 4 multiplied by RL. Got it? So if I take the common and everything, so we are getting Im square by 4 Rf plus RL as the IRMS or the total power for that matter, or we can say PAC is equal to Im square by 4 Rf plus RL. So this is the final expression of PAC. You will soon find why we are calculating AC. Okay, why we are calculating AC. The reason behind calculating this PAC is the very important parameter, as we call it, the efficiency. Eta is called as the power or rectifier efficiency. So the whole time that we were discussing about the uh, rectification efficiency of a half-wave rectifier. So this is it. So what that the equation of rectification is that DC power, DC output power to that of the AC input power. So this is the ratio, like how much it has converted from AC to DC. Okay, so that is basically the ratio. So in a way, we can say this is equal to PDC by that of PAC. And if I substitute everything what we have as of now, what was PDC? If I go back, PDC was Im square by RL by pi square. So we substitute Im square multiplied by RL by pi square divided by PAC. We have just now found out over here, which is Im square by 4 multiplied by Rf plus RL. Am I clear why we are doing this? Why we are doing all this calculation? Because as I said, we are trying to estimate the efficiency of the rectification. So for that, we need two powers. One is the DC power and the other one is the AC power. All right. I haven't told that earlier because I wanted to calculate and estimate and then come back to you to understand, to make you understand that what is the significance of these parameters that we are calculating. So for PDC, when we were calculating, we required IDC. IDC requirement was with respect to the IT, the total current which is flowing in the circuit. So based on that, we found out what is IDC. And similarly, we wanted to find out what is AC power. For that, we found out that the AC power is also can be countered similarly, and we can find out what is IRMS. Okay, and the IRMS is nothing but the AC current in that way. Like that is the AC equivalent of the current. So based on that, we substituted PDC and PAC. And if you go on computing this, it is coming around 2 by pi whole square RL by RF plus RL. And further, if I observe, that if I take all these 2 divided by pi, if I do it and take a square of it, this percentage of eta is coming around 0.406 divided by 1 plus RF by RL multiplied by 100, which is about 40.6%. So as I said already in the previous few classes that the half-wave rectification gives us a value of around 40.6% of efficiency, which is very, very low. If you observe that 100% out of 60%, if it is loss, like the total efficiency is not that good at all. So if the RF by RL, like usually RL will be greater than this we can write. Why? Because if RL is sufficiently greater than RF, as I said. So this parameter that you are looking at, this RF by RL is a very negligible parameter, this part. This is a very negligible parameter because RF is very small, RL is very high. So that is why we can write approximately that 40.6 is the about amount of rectification efficiency that we are observing. Any doubt? Any doubt, anyone over here? Please tell me. We started off from here and we ended up finding out why we are getting a 40.6% of power efficiency or rectification efficiency. But the important point is not to only note down 40.6 because that is fine. But the point is that in between, while solving that efficiency, we have come across some of these very, very important equations which will be used in different numericals and you will be asked to solve this. So please keep a track of all these equations which I have written over here. The basic objective is to take the ratio of DC power to AC power. We are separately calculating what is DC power. For DC power, we require the IM or the maximum current, and based on that we found out. And also to equate it in a way, we also found out an expression of AC power in terms of I maximum. All right, and based on that, we found out this is 40.6. Anyone having any doubt in this? Because in any way, the derivation won't come to you. As in an exam, derivation won't come. But in between, the equations based on those numericals can come. Okay, so that we'll counter. We'll see some questions also. We can understand how it will be dealt with. All right. So as of now, in this particular example, any doubt, anyone? Suppose I give you a small little task, like you can understand. Suppose you have if an applied voltage, please do it and tell me. See if I can understand that whether you are able to understand it or not. Suppose the applied AC power to a half-wave rectification is 100 watt, 1000 watt. Sorry. So this is my PAC. Oh, sorry, 100 watt only. Correct. 100 watt. All of you are following this? All of you are following this?
Yes, sir.
All right.
Yes, sir.
Suppose the AC power is 100 watt. The question is the DC power is generated around 40 watts. All right. So BDC is 40 watts. So naturally, my rectification efficiency eta will be nothing but 40 divided by 100, and this will be around 0.4, about that 40%, which we had just now proved. The question is, what happens to the remaining 60%? Can anyone like tell me what might happen?
Heat dissipation.
Is dissipation? Yes, it's because for the 40% that we are looking at, the 60% is lost due to the rectification circuit. But as you can observe that the 40% that you are observing, all right, that is due to the 50% is coming from the from the positive cycle, positive half cycle only. All right. So ideally, 50 watts is the positive cycle that converts to 40%. So you can see this 40% that you are getting. Remember, in half wave, what is happening? The top half, if you observe the diagram once again, so when this is plus, then only there is some output you are getting. So this part is completely negated. So already from the total supply, we are eliminating 50% of the power. We are losing out anyhow 50%. From the remaining 50%, 40% is the efficiency that we are getting. So don't think, though, you don't think that way that 60% we are dissipating. Am I understandable? From the 100%, 50% is not at all considered at all. So it is completely due to the half-wave rectification process. It's gone. All right. So that is not even taken into consideration. So when we are considering the total efficiency or the power rectification efficiency, and if it is coming 40%, it means this is the 50 watt, the 50, out of the 100 watt, the 50 watt, if I consider, which is due to the positive half cycle of the signal, out of the 50 watt, 40% is getting converted. So if we consider the power efficiency, suppose I consider a parameter power efficiency, how much it is. So this will be 40 by 50 multiplied by 100, which is around 80%. So if we consider the power efficiency wise, about 80%, the rectifier accepts only 50 watt and converts it to 40 watts of power. Clear? So this is the idea. Like for any half-wave rectification, that is the process. If you're asked to find out what is the total net efficiency, you might observe that it is already very low. But if you consider with respect to power efficiency, it is only working with respect to the remaining power that is there in the circuit. It's not that it's taking the 100 watt at all. Already from the 100 watt, 50 watt is gone, lost. Okay, so that is not taken into consideration at all. So that's why the 40% efficiency, rectification efficiency indicates that about 80% of power has converted. So this is just a small little example for that matter. All right. So hopefully this part of discussion is clear for us, all of us. Let me take another example, and after that we'll finish off this part of a few more parameters also. So suppose,
Sir,
yeah, please.
just to clarify, when in eta, when it says 40%, it's
Mm.
40% of the 100 watts that has been given in AC, which includes the negative half cycle.
Negative half cycle, yes. But
So the
uh,
40% means that but you said that the 40% does
hmm,
not include the 50% that is lost in rectification. I'm kind of confused.
acha, okay. See, the diode has a very small internal resistance, right? So it consumes very small power. So we are assuming that the power is not dissipated that much across the diode. All right. So
Yes.
now the 100 watt that we are considering, suppose it has two components. One is the 50% for the positive cycle and the 50% for the negative cycle, right?
Yes.
Now, as I'm what I'm meant to say is that as in case of half wave rectification, we are already, due to the circuitry itself, there is no chance of that negative 50% of the supply to come in at all in the circuit itself. So that is lost. That is not into consideration at all.
Oh,
Understood? That is not
yeah.
even considered.
So,
So
sir,
if so,
in
yeah,
in a very ideal diode, for example, where there is no
RF,
resistance,
RF, yeah.
would the eta would be 50%?
Uh, you can say that, but ideally it won't be. It in half-wave rectification, whatever happens, the cycle will be the half only. It can't be more than that because the internal resistance, what you can observe that the internal resistance won't affect that much. Like anyway, even if it is an ideal diode where there is RF is minimum, so that will not affect the diode performance or the rectification performance. It might improve a little bit, not like 50% will happen. It might improve a little bit, I can say. All right, but in a general, in half wave rectification, as we are eliminating a half of the cycle, like half of the signal itself, and there is no provision of it, so you cannot say that it will improve anything. Maybe a little bit of percentage improvement might happen, but that is insignificant, to be honest. That's not that huge.
But then, sir, I don't understand why it's not 50%.
Why it is not 50%? So in that case, what will happen though? So what you are asking is like PDC, it is 50 watt. like 100 watt of PAC is there, and PDC is 50 watts. Like this you are
Yes,
wrong,
because
right?
half the cycle is getting eliminated.
But here this
The
10%,
dissipation is minimal.
this 10%, the 10 watt of reduction that is happening, that is not due to the diode. It's due to the RL, the resistance that you are using, right? The load
Oh,
resistance is also is there, right? Because if you go back that when we are calculating PDC, RL is a factor.
yes.
All right.
Okay.
So you can say that if RL can be controlled by some means, then maybe we can have a PDC which can be changed in a way. So then the 50% of current might come. Understood? So that is how it can be linked, you can say. But
Okay.
if even if it is an ideal diode, it doesn't make, because in the equation RF is not a factor at all. We are
Okay, I understand.
understood. So if you are
Yes.
so that is how we are going to consider. But anyway, for a circuit to not to like get heated up or not to deliver properly, you have to keep certain values of RL. You cannot exceedingly, you cannot keep it very low or you cannot make it very high. It's a load resistance because you have your device which are connected to it, right? So that will be affected due to the change in resistance. So you cannot like for a suppose you are using a half wave rectification and you want something to boost, like a boost in a different way altogether or efficiency, you cannot do that. Actually the circuits will not allow, the elements won't allow to happen. All right.
Okay.
All right.
Okay. Thank you, sir.
Got it. Good. Good. So this is one half of the story, and maybe another question I can, if I can squeeze in, because it's a little different question, and hopefully some of you might also answer. Those who have done the lab on Monday's lab, I think those people can at least try to answer this. The question is, I'm writing a little bit, an AC supply. Okay, this is also based on half wave rectification. An AC supply of 230 volts is applied, okay, through an HWR, stands for half wave rectification circuit, where a transformer is used with, this is a new term for all of you, with turn ratio, transformer turn ratio of 10:1. For those who have not done the Wednesday's class, like tomorrow's class, I'll explain you in lab also what exactly is 10:1, 1:10, like that. But for Monday's batch, this might be a similar term. So 10:1. Question is, first of all, find the output DC voltage. And second part we are not going to do, but anyway, I'll write it down. What is the peak inverse voltage? To understand the second part, we'll see a few more portion, and then we'll discuss of the peak inverse voltage. So this is about the question. Now, suppose if this type of question is coming in, then we have to consider. That the primary to secondary winding. So this is a turn ratio. So let me just write down that turn ratio. This is a new thing. It is not related to diode by any chance, but it is related to transformers. So this is given by N1 by N2 is equal to 10:1 or equals to 10, where N1 is usually called as the primary to primary winding, number of windings in the primary cell, and N2 is the winding in the secondary inductor. All right, so this is the turn ratio, we call it N1 by N2. And why it is so important? Because usually V secondary, please make a note of this, because this is again not related to diode or any means. So V secondary, what is primary secondary? Just to make you understand, this is the primary part, and this part is the secondary part. This is how the transformer behaves. So primary to secondary winding, that how many number of turns will be here, that is given by the primary to secondary winding. All right. So that given by, so you can see the voltage across this part, the secondary part. So that's V secondary, I'm writing over here. V secondary is given by square root of V RMS voltage. Remember, for people who are there in Monday's class, I told you if 230 volts of supply we are supplying, which in this case is, we have to multiply by a square root, and that will give us a value of 325.3 exact values. Remember, in lab we have done it with respect to 308 volts for that matter, approximately. And the same logic I told you, that whenever we are using in a transformer, definitely the voltage across it will be a square root or RMS value of it. So square root of the RMS value, and that is coming around this value. So this is the voltage actually across the supply that we are getting. All right. Sorry, this is a primary voltage. I'm just very sorry. This is the primary voltage we are getting. This is the primary voltage. Primary voltage. So what does that mean? So 230 volt is supplied over here. So after this region, if I just happen to write it about this region, about the coil, the voltage is actually 325 and not 230. Okay, so that is given over here. So this is my primary voltage. So this happens to be the source to the next circuit. So V secondary will be nothing but N1 by N2 by N1, that is N2 by N1 multiplied by V primary. Please make a note of this. So this is 1 by 10 multiplied by 325.3 volt, and that is coming around 32.53. Okay, so the question was find the output voltage. Find the output voltage. So VDC, see in this particular question, we actually have the consideration of we know the equations. So can you tell me, if I go back to VDC, which equation we are going to use for that matter? If I go back here, any specific equation that you observe that we can use? Can I write it over here? VDC, IDC is Im by pi into RL. So this is one of the case. All right. And also in terms of our case for this transformer equation, as is mentioned over here, VDC is nothing but V secondary divided by pi. All right. Because IDC into RL and IDC is equal by Im by pi into RL, and that Im by pi. So Im into RL, that nothing but V secondary. Why? Because this is Im into RL by pi. Okay. So this part is equivalent to the secondary voltage, because secondary voltage appears where? Secondary voltage appears somewhere here. So that is basically the current which is flowing in this segment of the circuit. All right. So if I happens to write that, so 32.53 divided by pi, which is around 10.36 volt. All right. So this is about the voltage across the OBDC that we are looking at. Negative cycle, naturally the diode will not conduct, so the voltage across the diode will be total peak to peak voltage. If I peak inverse voltage, if I consider, that will be 32.5 volt only. All right. So this is one of the segment of our discussion. So end up to that, two factors we are left with, which I think I should tell you. One is called as the ripple factor, very important factor, ripple factor. I'll just quickly summarize this. Ripple factor. Okay, and the ripple factor is given by R, and that is given by RMS value of AC component. This also, I think, will be more clear to the people who have done the one day's lab, because I have shown you how this ripple factor can be reduced also. And this is called as average value of AC component. So what does that mean? This is given by IRMS if I consider. Okay, so IRMS will be given by something like this, square root of, again, you don't need these steps, but just for my own understanding and as of now. So this is basically IRMS. It's a combination of the DC supply, the DC current, as well as the I1, I2, which are the ripple components of the fundamental harmonics. That is one fundamental harmonics will be there, and there will be multiple ripple. Ripple is nothing but like repetition of the same thing, multiple reflection kind of, you can say. So that square root, if I consider, that will be IRMS ideally. All right, and also we know IDC already that is equal to Im by pi. We have already established from equation number 7 maybe, I think. All right. So R is given by square root of I RMS square minus IDC square, because you can see this square, if I do the squaring, if I do it on the both side, I RMS square minus this part IDC square is given by the portion over here. Can you understand this? Can you understand this? Why I'm doing this? IRMS square minus IDC square is nothing but this factor I1, I2, I3 up to IL, which are nothing but this part is nothing but the ripple components, which actually will create the problem. All right, because usually when you are supplying an AC and you are getting a DC supply, you are supposed to get a steady state value. But this ripple component, if it is too much, then means that it will not be a steady state output. So that is why we require the calculation of this ripple factor. So the ripple factor is given by I RMS square minus IDC square divided by IDC. And if I reduce this a little bit, it's coming as I RMS square by IDC square minus 1, or rather I would take a whole square maybe. I'll take a whole square. So this is whole square minus 1. So if this is the equation, we'll take the last minute. R equals to. So if you remember, I RMS was given by Im by 2. Remember, I already had proved it over here. If you go back a little bit up, yeah, here, Im by 2. Okay, so IRMS is Im by 2. Okay, and IDC is Im by pi. So you take the ratio. So R is given by square root of Im by 2 whole square divided by Im by pi whole square minus 1. And this is given by pi by 2 pi by 2 whole square minus 1. If you substitute everything over here, Im get cancelled, pi comes up. So pi by 2 whole square minus 1. And after you calculate, it will come around 1.21. Now this 1.21, what it indicates is that the amount of ripple that will happen with a half wave rectification will necessarily degrade the output to a certain extent. Okay, so the condition is that the more we want to get a better output, we need to reduce this ripple. And to eliminate this ripple, as I pointed out in the Monday's lab also, we can use some capacitance in parallel to the load resistance where the ripple can be reduced and we can get a steady state response. For that to prove, I'll show you in the lab. For people who have not done it in Wednesday's lab, I'll do it. But for others, for the Monday's batch student, you can understand that basically the ripple factor is a factor by which the steady state response we are not about to get. But if I use a capacitor in parallel to it, we can reduce this to a certain extent. And that's more like it. And there is another parameter you can keep a note of, which is called as voltage regulation, which is given by VNL minus VL divided by VL. This is called as the voltage regulation in percentage. So what about the diode? When the diode is being used or the half wave rectification is used, this is called as voltage regulation. Maybe I'll stop it here so that we can come back and discuss this. This is not that difficult or not that important for a normal diode, because as we know that the voltage regulation is mostly done by a Zener diode. So, but the equation is something like this, and ideally VNL, this is given by no load no load output voltage. This NL stands for no load output voltage, and VL is with output voltage. Okay, with output voltage. And this VNL is also mentioned as Vm by pi, can be derived as Vm by pi. And this VL is given by VDC minus IDC into RF plus RS, like this. Whatever it is, the final outcome of this is VR is RS plus RF by RL into 100, where this RS is nothing but a series resistance which is connected to a diode while it is used as a voltage regulation, which is not needed. As I said, it is not that important as of now, but this is the equation that finally we get of the voltage regulation. All right. So many informations over here for today, and this is for the half wave. Similarly, for the full wave, we will get a similar kind of trend, which I will explain on next day's class, as well as doing some very important numericals on Fridays. Friday, I think we don't have a class, but on Saturday we have a class, so we'll continue at that point. All right. So let me stop sharing, and I think I already have kept you waiting. So sorry for that. We'll meet again next day. Thank you.
Yes, sir.
Thank you.
sir.
Thank you.
Thank you, sir.
Thank you, everyone.
Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.